We are live.
A very good evening, everyone. Thank you for joining us in the fourth session of PROTOLITH 20's webinar series. I hope you have had a great day till now, and we are set to make it even better henceforth. I, Mohali Das, on behalf of the entire team of PROTOLITH 20, welcome Professor Hugh Rollinson to deliver a talk on the origin of Earth's continental crust, geochemical insights. Without further ado, I would request our distinguished faculty, Professor Shakti Saravan Chinnasamy, to briefly introduce Professor Rollinson, extend warm greetings on behalf of the Department of Earth Science Society, Bombay, and take the program ahead.
I welcome Professor Rollinson to the webinar series. Professor Hugh Rollinson is co-director at the Faraday Institute and Emeritus Professor of Earth Sciences at the University of Derby. He is a remarkable geochemist whose primary work has been centered around the petrology and geochemistry of arcane rocks and crustal evolution. After graduating from Oxford University and prior to his PhD at the University of Leicester, he served as a field geologist in the Geological Survey of Sierra Leone for several years. After pursuing a postdoc from the University of Leeds, he has worked at the universities of Glasgow, Zimbabwe, Sultan Qaboos University, Oman, and more recently as Professor of Earth Sciences and head of the department at the University of Derby. I'm certain that our audience is well aware of one of his many celebrated books on geochemistry titled Using Geochemical Data, Evaluation, Presentation, Interpretation, which is a summary of his extensive work on geochemical techniques used to interrogate ancient rocks. We can go on and on about his contributions to geochemical field and not to get tired, but the time is limited, so I may now request Professor Rollinson to begin his lecture. Professor Rollinson.
Thank you very much indeed. Thank you. I'm going to share my screen now and use some PowerPoint slides to illustrate my talk. Just wait for this to come up.
Yes, sir.
Okay, so can you hear me clearly and can you see my shared screen?
Yes, sir.
Good. Okay. So thank you for your welcome, your introduction, and your opportunity to speak to you in India. You might be interested to know that in England at the moment it's extremely cold and it started snowing this morning. So I suspect we are in a different temperature zone from where you are. Anyway, my topic this afternoon is to speak to you about the origin of the Earth's continental crust, and in particular how we might understand this process using the techniques of geochemistry. So if we look at our own planet in the context of the solar system, let me just set my laser pointer. If we look at our own planet, the Earth, in the context of the solar system, we see that there are 4 rocky planets and then there's the asteroid belt. But amongst them, the Earth is the only planet which has an extensive continental crust. And we may wish to ask ourselves, why is this? Why is the Earth different from those other planets which are seemingly the same in composition in the way they have been made in the early solar system? And so what I'm going to do in this talk is I'm going to talk to you about 4 separate themes which seek to help us understand the origin of the Earth's continental crust. First of all, I'm going to talk about how we might use the average chemical composition of the Earth's continental crust to help us understand its origin. I'm going to talk a bit about how we might calculate the Earth's growth history in order to understand the history of the Earth's continental crust. And then I want to focus particularly on the very early history of the Earth's continental crust, something that I spent quite a lot of my own career thinking about. And by the way, as we begin to think about this subject, we find ourselves delving into the question of when did plate tectonics start on Earth. So that's a subsidiary issue, but a hugely important scientific question. And then to finish with, I want to bring you up to date on some of the new developments that have been taking place in this field over the last 3 or 4 years. So the first theme I want to develop then is to look at the origin of the Earth's continental crust through the lens of the average composition of the continental crust. So how might we estimate the average chemical composition of the whole of the Earth's crust? Well, let's take a continent. In this case, I've taken the continent of South America. And we can see that this piece of crust is made up of a number of different components. We've got some young granitic crust in the Andes. We've got old granitic crust in some of the ancient shield areas of South America. And overlying them, we've got areas of sediment. We need to find a way of integrating the chemical composition of these different components to give us an average composition of this area of crust. However, these are the rocks which are just at the surface. We also need to look at the rocks which are beneath the surface. So we need to also include the lower continental crust to get a true composition of a crustal average composition. And this was a technique that was first initiated by a geochemist, Roberta Rudnick, and a geophysicist, David Fountain, who back in the mid-1990s used a combination of techniques, geophysical and geochemical, to look at the chemical composition of the different layers of the crust, and from that obtain an average for the whole of the Earth's continental crust. Now this diagram is based on some information from China, but we could do this across the whole of the Earth, and we could produce a weighted average composition of different types of crust comprising different layers to give us an overall global average from the many different tectonic settings that we find. You'll note that cratonic areas where the crust is very thick and tectonically active areas, basins, are very different in their nature. And so we need to integrate all this information to obtain an average composition of the Earth's continental crust. Now, what this has led us to is an acknowledgement that if we plot the chemical compositions on a very simple silica versus alkalis diagram, and this is the classification scheme for volcanic rocks, we see that many estimates for the average composition of the continental crust lie in the andesite field. And the Rudnick and Gao estimate, R and G, is here, and that's one of the most reliable estimates that we have now, following on from Rudnick and Fountain. Now, at first sight, if we take the average composition of the Earth's crust as andesitic, that would suggest that the Earth's crust formed in some kind of arc, implying tectonic processes consistent with modern plate tectonics. However, there is a problem with this solution, because we find that when we look at the processes that take place with an arc, andesite is not the primary melt of the mantle when we explore an arc. If in this cartoon diagram we look at where mantle melting is taking place, it's taking place in an arc because of the dewatering of the slag. Melting takes place in the mantle wedge, and the primary melt that is produced in this process is basalt. And so processes in an arc do not produce andesite as a primary product, they produce basalt. And andesite is a derivative product from this process. And so the primary basaltic melt is fed into a series of magma chambers from which ultimately andesite is produced in the creation of an oceanic arc. And so andesite as the primary process which makes continental crust is not helpful. And we need to look more carefully at this process in order to understand what's going on. So if we go back to our alkali silica diagram and look at the field of average continental crust today, we need to also consider the composition of crust from the very early Earth, because we find that this darker blue patch here, entitled average TTG, I'll come on to explain that term in a moment, we find that the average compositions of older crust are much more silicic than the crustal average which we have today. And because of this, they imbalance the crustal average. And so what we find is that if we take the composition of an average arc basalt, the product of melting in an arc, and we take the composition of ancient continental crust and mix them together, that is how we can derive an average crustal composition that is andesitic. In other words, the average andesitic continental crust does not tell us about a primary process. It tells us about a mixing process between two different end members. And one of those end members, which I'm going to come back to during the talk, is the nature of average continental crust that formed in the early Earth. I've called it here average TTG, or if you like, average Archean crust. We need to take note of this composition, and we need to be inquiring how this composition was derived. So, understanding the average composition of the Earth's continental crust only gives us a partial solution to the origin of the Earth's continental crust. So let's turn to another theme now, and let's look at the growth history of the continental crust, because here the combined use of geochemistry and geochronology can give us some very important information. If in this case we take North America as an example, this coloured map shows us that the continent of North America has grown over geological time. We can see that the red area in the northeast of the United States and in Canada represents the oldest rocks forming the cratonic rocks of the Canadian Shield. And then adjacent to that we have, in blue, we have Proterozoic rocks. And then as we progressively go over to the west coast, we find lots of young rocks which have been accreted onto the margin of the continent in relatively recent geological times through the process of arc accretion. And so we have from here a very simple example of the fact that the continental crust has grown over geological time. And what we need to try and ascertain is to what extent and to how rapidly this has grown and how the continental crust has grown over Earth history. So in this diagram here, I'm showing you some of the different ideas that people have about how the continental crust has grown over time. So we have a graph showing geological time from the present day on the left here to the beginning of the Earth on the right. And on the y-axis, I'm showing you the fraction of the amount of continental crust that has actually grown over geological time. And you will see from this graph that there are many different models. You will see, for example, that the amount of crust which is observed of different ages is very different from many of the different models that we see. And there are two basic types of model. There are models which imply the Earth's continental crust grew very rapidly over geological time. In this model, the one by Dweem and others, published in Science in 2012, we see that maybe 70% of the Earth's crust had been formed by about 3 billion years. There are other models which imply the continental crust grew more progressively, and this one by Condi and Astor is based on what we regard as pristine, newly formed crust, implying a series of bursts of continental crust growth over geological time. So we have a problem here, because sometimes as we look at these growth curves, what we really want to know is how much new crust has formed over geological time, and differentiate that from older crust which has been reworked or recycled. And this is a very tricky problem, because we have a number of calculated estimates of newly formed crust, such as those by Dweem, Robertson, Spencer, Belousova and others, which all indicate a very large amount of crust had formed early in the history of the Earth. This is contrasted with the observed amount of crust which we find today. And the disparity between the two we may describe as missing crust. Crust which is supposed to be there, but crust which is not observable. And we may put that down to ancient crust which has either been reworked, that is, old crust has been partially melted and now has a younger looking age, or crust which has been recycled, that is, it has been created and then it has been returned to the mantle. Now, my own personal analysis of this rather complex problem is described in this paper in 2017 in the journal Geosphere, produced by the Geological Society of America. And I would argue that those authors who want there to be very large volumes of crust in the early Earth are misreading the data, and that there were no very large volumes of felsic continental crust in the early Earth, but rather we need to employ a curve rather like the curve of Condi and Astor, which suggests that the Earth's crust grew progressively over geological time. But even so, when we look at this curve, we can see that a significant amount of new crust had formed early in the history of the Earth. And so we could argue by 2.5 billion years ago, the end of the Archean, already up to 35 to 40% of the present continental crust had formed. And this is a very significant volume of crust that has formed early in Earth history, and we need to take note of how this crust formed. So what I'm saying is, if we look at the average composition of the continental crust, we see that we need to take account of early crust in order to fully understand the process. And if we look at the process of crustal growth, we also need to look at how early crust formed in order that we might understand the true origins of the continental crust. So this is where we move to theme 3 and talk about the nature of the Earth's earliest continental crust. Now here, of course, we are probing deep into the past, and so there is very limited data that geophysics can give us on these rocks and on these processes. We can't explore modern processes in subduction zones and spreading centers and so on using geophysics when we go back in Earth history. And so this is where geochemistry is extremely important and can really help us. So when we look at the nature of the very earliest continental crust. We find the rocks scattered all over the globe. So the areas in black are those where we find these ancient rocks, Archean cratons as we call them, and you will see very substantial amounts of these rocks in India. Here's an example of a relatively undeformed example in the UK, in the northwest part of Scotland, where we see the rocks, felsic gneisses, forming ancient crust of about 2.7 billion years ago in what we call the Lewisian gneiss complex of northwest Scotland. In fact, a tiny, tiny fraction of the total amount of ancient crust preserved today. But if we look in other parts of the world, we find very similar rocks. So this is another image of the rocks in Scotland. This is an image of some rocks I looked at many years ago in West Africa. We find deformed examples in South India, and I'm sure you'll be familiar with many other examples, and deformed and migmatitic examples when we look at Central Africa, such as Zimbabwe, for instance. Now, when we look in detail at what these rocks are made of, we find that they're granitoids. They're granitoids with rather unusual compositions. They have the composition of either tonalite, trondhjemite, which I'll explain in a moment, or granodiorite. And because of this trilogy of names, we abbreviate them to the acronym TTG. These are the rocks of the TTG suite, and these are the rocks which characterize the nature of the Earth's earliest continental crust. We can represent their compositions on a classification diagram like this. You will see that we are using the components anorthite, AN, albite, and orthoclase, the different components of felspar, and we are doing what we call a normative calculation on a rock composition to produce this normative felspar diagram. And what we find is that we can classify granitic rocks using this diagram based on their normative felspar content. So, for instance, tonalites plot in this field, trondhjemites, which are tonalites without much mafic component, plot down here, granodiorites plot here, and granites with a higher potassium felspar content plot over here. And the average composition of Archean TTGs plot in this field here, somewhere between the tonalite, trondhjemite, and granodiorite compositions. And I haven't drawn it on, but about here where my pointer is the average composition of the Earth's continental crust. And we see that the Archean crust is more sodic and less calcic than average continental crust. So if we think about how TTGs might have been formed and where have they come from, we can plot the data again on this diagram, and you will notice a great area of overlap between the average composition of TTGs and the field of partial melts of basaltic rocks. So if you take a basaltic rock and melt it somewhere between 10 and 30%, you will generate a felsic melt. And that felsic melt may be tonalitic, trondhjemitic, or granodioritic, or even granitic. And so we see an overlap between the composition of TTGs and the partial melt of basalts, implying that TTGs are most probably the partial melt of basaltic rocks. Certainly, they are derived from a basaltic parent. When we look in detail, and this is a result of experimental melting, we find that in order to create this melting, to produce felsic rocks, there needs to be water present. So there has to be wet melting. So it's normally melting of a wet basalt, an amphibolite may be, a rock which has got water in its crystal structure, which gives rise to the synergy between TTGs and partial melts of basalt. And here's an example in the field. This is again from Scotland in the United Kingdom, where we find veins of TTG material penetrating older basaltic rocks. These are amphibolytes, they're a little bit epidotized, slightly altered, and it's possible when you look at these rocks carefully that you might see the hint of pillar lavas. It's quite possible that this is original basaltic material, which was the source rock, which melted to produce the TTGs which we find in this area, confirming the idea that TTGs are the melts of a basaltic parent. But when we look in detail at TTGs, we find that they form a series of subgroups. And this is a trace element diagram using cerium over strontium versus yttrium. And we can see that TTGs might be subdivided into a high pressure group, this lower category, a medium pressure group with the grey ring, or a low pressure category. And this is based upon their trace element content, but is thought to reflect different pressures of melting. We can see it in the rare earth elements too. The low heavy rare earth TTGs are thought to represent garnet in the source and high pressure melting, or high heavy rare earth element TTGs, they're representing low pressure melting. So bear in mind that there are different types of TTGs representing different types of melting process at either high pressure or low pressure. And this leads us to, I think, to some thinking about the origin of these rocks. How might the partial melting of basalt taken place in the early Earth, and what are the implications in terms of former plate tectonics? So here's a model suggesting how we might produce TTGs by the partial melting of hydrated ocean lithosphere. Remember, in the Archean, the Earth was much hotter, so the mantle was hotter, and so when we had subduction, if we had subduction, it's very likely that instead of the subducting slab being dehydrated, it actually melted. And so we have here a melting zone related to the subducted slab in the mantle, from which TTG melts are created and Archean continental crust is formed. However, there is another model, and that is based on a huge amount of basaltic crust, which we think was present early in the history of the Earth. And it's quite possible that we have had a situation such as a plume, a mantle plume, which has produced huge volumes of basaltic lava, rather like the island of Hawaii in the Pacific today. And this huge thickness of basaltic lava became so thick that it began to melt at depth, again assisted maybe by a hotter than present day mantle. And so we may have had at the base of this thick lava pile a partial melting zone in which TTG melts were created and new continental crust was formed. So these two models have very different implications in terms of tectonics. The first model would imply plate tectonics in the Archean and would require melting at a very high pressure, maybe 20 kilobars or so, at a depth consistent with subduction in which the melting of the slab could take place. Alternatively, we may have had much thinner, shallower, shall we say, melting at a lower pressure, but melting of a thick lava pile produced in a plume, or as some people describe it, in a stagnant lid of basaltic magma that was produced very early in the history of the planet. If you look at the moon, you see a basaltic crust on the moon, because the moon lost its heat, its thermal energy very early on in its history. Nothing much else happened on the moon. The Earth may have been similar in its earlier stages. It may have started off with a very thick basaltic crust, perhaps basaltic lavas akin to those of mantle plumes that we see today. But in order to melt that we probably didn't need to go to the depths that we do with subduction. And so this process will be characterized by low pressure melting. So we actually have a means of attempting to discriminate between these two models, looking at the difference between high pressure and low pressure melting, and whether we can see a signature of that in the chemistry of ROCK and TTGs. However, we have a problem here because some TTG suites appear to show the effects of both high pressure and low pressure melting. Now, this is a problem if we are trying to use the difference between the two in the geochemistry to discriminate between two models. It gets worse, as I'm about to show you now, as we look at some more recent developments in this field. First to note, though, that the two groups who would advocate the different models are both alive and well. Tim Johnson, who's now in Australia, argues there was no subduction when the first continents were formed. A Japanese group working in Labrador would argue that there was plate tectonics very early in the history of the Earth. So what's happened most recently, which might help us resolve or not resolve these problems? Well, I want to talk to you about three new developments which have taken place in the last 3 or 4 years. The first one is the results of what we call phase equilibrium modelling, which has been used to try and help us understand the origin of melting processes in basalts. Until recently, until about 5 years ago, if we wanted to understand the melting of a basaltic rock to produce a TTG melt, we had to conduct an experiment in the laboratory. In fact, we had to conduct many, many experiments at different temperatures, at different pressures, and using different starting compositions and different amounts of water. Now we have a technique which allows us to bring together all the thermodynamic evidence that we have from these melting experiments and build a certain thermodynamic model. And this is what Richard Payne and colleagues did in 2016. They took phase equilibrium data from all the experiments that had been conducted on basaltic rocks and produced a phase diagram in pressure and temperature space showing the stability fields of the different rock types that are produced when a basaltic rock melts. On a diagram like this, we've got a melting curve here, this heavy black line. So the right of this curve, we have melt coexisting with these different residues. Here we have the stability field of garnet, shown in red. So rocks with garnet sit above this line. And so we can begin to ascertain from geochemistry and from the stability of phases preserved in the residue of melting what the melting conditions might have been if we melt a particular basaltic rock. Now, this study was based on an average Archean therlite, and what's known as the average enriched Archean therlite. And this phase equilibrium modelling was used to estimate the conditions of melting. It requires an assumed starting material and an assumed water content. And from the calculated compositions, it was estimated that the optimal pressure temperature conditions of melting is in this temperature range and at this depth. Not mega deep, not extreme deep, not the high pressures required in a subduction zone, leading to the suggestion that the partial melting required to produce Archean TTGs took place in an oceanic plateau, required some kind of plume model. Now, a similar study was carried out by Johnson and others, where they used a very specific example. They used 3.5 billion-year-old basalts from the Pilbara Craton in Australia, and they produced a very similar diagram. from their data, they suggested that, again, melting took place in a thick crust and there was no need for subduction. Their calculated stability field is slightly shallower and their temperature is slightly higher than the data of Palin, but it basically amounts to the same thing, that using this phase equilibrium modeling technique, then we have no requirement for subduction, implying that basaltic melting took place in some kind of thickened basaltic crust, produced maybe by a mantle plume. However, there needs to be some discussion of these results, because particularly the Pilbara samples utilised rather unusual starting materials. The basalt used in the Pilbara experiment is not a typical Archean basalt, and one which I would argue it will not be present on the Archean Earth in any great volume. The trace element data are ideal. They're perfect for modelling the origin of Archean TGs. But again, they are not typical of normal Archean zodiacs, but they do allow us to test this model and produce typical TTGs, as is seen in this diagram, which I've extracted from their paper. Let me take you to another development which has taken place very recently. This is a paper that was published earlier this year and is taken from a study in South Africa. We have here some rocks from the Barberton area of South Africa, and they examine a TTG pluton known as the Stolzberg pluton. Nearby, amongst the basaltic lavas of the Barberton Greenstone Belt, are some rhyolitic lavas. And the finding of these authors, Lauren and others, suggests that these Stolzberg TTGs are coeval with these rhyolites, these felsic volcanics, which are found nearby. And these authors carried out some very clever and intricate zircongeochemistry in order to establish the coeval nature of these two suites. What they suggest is that we have a pluton here where we have a primary parental liquid, and that liquid differentiated in a magma chamber into a suite of TTGs and some volcanic rocks which appeared at the surface. So what they're suggesting is, from geochronological and geochemical evidence, is that the TTGs of this area are plagioclase-rich accumulates and the rhyolites are derivative melts. Now, the implications of this suggestion cannot be overstated. I'm showing you the data here again on an anorthite albite orthoclase diagram. We have a suite of trondhjemites and granites here. We have some parental diorite material here and parental liquids shown on the yellow stars here. And we have these felsic melt intrusions, felsic melts, found as melt inclusions here. So what we're saying is that the TTGs that we're looking at in the Stolzberg pluton are the product of fractional crystallization. They're derivative melts, and from them has been removed a rhyolitic melt. And the compositions that these melts show are controlled by what I've called a plagioclase control line, which is shown by this black arrow here. The implications of this finding are that any TTGs that we look at may not be primary melts. In other words, they are derivative liquids representing plagioclase accumulates or hornblende enriched accumulates from which a felsic melt has been extracted. Now, if this is true, then everything that we have done with Archean TTGs is invalid, because we have not been dealing with primary melt compositions. And the work of these authors, Lauren and others, published in Nature Geoscience early this year, have attempted to calculate the liquid from which the TTGs came and the primary parental liquid, which is this upper star here. Now, interestingly, last year, some Chinese authors, Liu and Gao, produced a very similar argument, but based it on a different line of reasoning. Their data was from the North China Craton, and they suggested that TTG compositions were also controlled by a hornblende or hornblendite control line, so that in their example, compositions are spread in this part of the diagram. So we have further evidence that TTG compositions are not actual melts, but are the product of fractionation processes using either hornblende or plagioclase. So this has serious implications for our thinking about the nature of the continental crust. Now, you could argue that the work in South Africa was done in the upper continental crust and therefore may not be relevant to the deeper crust. So recently I've been putting together data for the Lewisian complex granulite facet TTGs, which I've worked on in the past, and we see the same thing. We see rocks showing a plagioclase control line, and we see rocks showing a hornblende control line. And so the South African example is not atypical. It looks as though this process is widespread throughout our understanding of Archean crust. And what it means is that we cannot just take the composition of TTGs and use them how we like. We must use them to derive the composition of the parental liquid from which the TTGs are developed, or have evolved. My final comment about new developments comes from, again, some work that was published in Nature Geoscience in 2019 and involves the use of silicon isotopes. Now, the study of silicon isotopes depends upon fairly recent developments in ICP technology, where ICP mass spectrometry has allowed us to analyze a raft of new isotope systems, and the stable isotopes of silicon are one such system. In this case, we measure the ratio of the isotope silicon-30 to silicon-28, and this is expressed on the silicon isotope diagram as delta silicon-30 as in parts per thousand. And what has been found is that Archean TTGs are different from most other crystal granites. And the short version of this rather long story is that suggests they've been produced from a source which is contaminated with chert sediment. If you look at this diagram here, you will see that Archean TTGs are enriched in their delta silicon-30 by a tiny amount. Notice that the scale represents a very tight scale in the silicon isotope range. So there is not much variability between different rock types, but Archean TTGs are distinctive in being enriched in their silicon-30 content. And how might this have come about? Well, one of the most enriched rock types that exists, enriched in the heavy isotope, is chert. And so the suggestion is that maybe Archean TTGs have come from a source which contained chert. Now, what might this look like? If we now take our data and put them on a stable isotope diagram using silicon and oxygen isotopes, we get a diagram like this. So we've got silicon isotopes along the bottom, we've got oxygen isotopes on the source, on the side, and we've got our potential basaltic source from which we make TTGs here, and we've got various mixing curves. And the mixing curve that works best to produce Archean TTG compositions is one which involves sedimentary chert. So in other words, we've got a basaltic source which includes sedimentary chert. So it looks as though our Archean TTGs, on the basis of silicon isotope sediments, were from a source which was enriched in silica. In other words, a silicified basalt. Now, where might we find this in abundance? Well, the argument goes, this represents Archean ocean floor. But the basaltic source for Archean TTGs was silicified Archean ocean floor, in which case Archean TTGs were made through subduction processes, because this is how we could make this most efficiently. However, in my view, there are problems with this, because this feature is found on Archean TTGs right throughout the Archean and into the Hadean, implying this process was widespread, which implies that subduction took place in the Archean throughout the Archean and from the Hadean. And from my mind, that is highly improbable. So we are left with the question, could this fractionation be produced by some other, maybe igneous related process, rather than the mixing process, which is advocated? So what I've been trying to say in this talk is that amongst the rocky planets, our planet, the Earth, is unique in having a continental crust, and our understanding of the origin of this crust comes through the techniques of geochemistry. Much of this crust was formed very early on in Earth history, in the first 3.5 to 2.5 billion years, through the wet melting of older basaltic crust. But whether or not this took place through plate tectonics is still a contested argument. The presence of water on the Earth, though, seems to be the key. Now, before I conclude, finally, let me just advertise a couple of books which you may well know. My book on using geochemical data, which is been published a long time now, and a book that was published about 13 years ago, Early Earth Systems, in which I talk about the origin of the Earth's continental crust and many other aspects of the early Earth in much detail, published by Wiley Blackwell. But you may be interested to know that over the last year or so, I've been working on a new edition of Using Geochemical Data, a second edition, which will be published by Cambridge University Press in the summer of this coming year, 2021. It's an expanded version of the old book. It's completely updated. Many sections have been completely rewritten. There are new and improved diagrams in colour in the book, and I've co-authored it with Professor Victoria Pease from the University of Stockholm, who is Professor of Tectonics and igneous geochemistry at that university, and so very well qualified to assist me in providing an updated edition. So thank you for your attention, thank you for listening, and I think now we may have some time for questions.
Thank you so much, Professor Rollinson, for such an engaging and enlightening talk. It's an honor to have you here with us today. So, shall we address a few questions asked by the audience? So, shall I go on? So, am I audible? Hello?
Sorry, yes, please go on if you're asking me. Yes, yes.
So the first question is, vanadium is affected the least during the fractionation processes, but what is the interpretation for any significant V anomaly found in the rocks? Can this be correlated to earlier conditions?
Sorry, you'll have to. What sort of anomaly are we talking about? REE anomaly?
So, vanadium.
So, I think if we look at vanadium, it's basically telling us about oxidation conditions in the Earth. And so if you look at vanadium in basaltic rocks, for instance, we would be looking at whether the mantle was more or less oxidizing in the early Earth than it is today. And in my view, from work I've done on chromite, not on vanadium, suggests that the Earth's mantle has had a very similar oxidation state from very, very early on in Earth history, certainly from about 3.8 billion years up to the present day. So I would argue no change.
Okay, so thank you so much. The second question is, what are the geochemical effects of crustal growths on the crustal roots that are believed to host diamonds?
So I think as the crust has grown, we have moved from a broadly granitic component to a broadly basaltic component. So as we look at crust today, we find the addition of basaltic material, and we add that to early granitic material, and that then gives us the average composition of crust, which we see today, which I mentioned in the early part of my talk, when I was talking about using crustal composition to work out the average composition, to work out the origin of the continental crust.
Okay, thank you so much, sir. And the final question is, to get the proxy for the thickness of paleocrust, can the LRE be used to interpret the Archean conditions as well?
I think if we want a proxy for ancient continental crust, I'm not sure that we can use the light rare earths. When melting takes place, the minerals which control the melting will be governed by the depth at which they form. So, for instance, if garnet is present, in different rock types, garnet will appear at different depths. In basaltic rocks, it's quite a number of kilometers down, it's several kilobars down before we can actually see garnet coming in. In the felsic crust, it's much more variable, depending on the composition of the rock type. So I would argue that we would need to think about other proxies of melting before we could work out the thickness of the paleo crust. One of the things I think we do need to take into account is not just the crust, but the underlying mantle. And so the nature and the thickness of the subcontinental lithosphere is equally important as the nature of the paleo crust. Of course, we've got obvious things like metamorphic conditions. And so if the crust is a granulite grade, that then gives us some idea of the nature of the thickness of the paleo crust. And there are many areas of Archean crust which are at granulite grade, and so they are a suitable indicator of paleocrystal conditions.
Thank you so much, sir. Now I would request Professor Chinnasamy to conclude the session.
Fine, thank you.
Thank you, Professor. Before I would like to thank, I have one question. One of the slides you showed that the church and BA was clubbed together, and having del 30S is about, del 30SI is about, it's quite a lot varying. Can you explain why this BIF is having a lot of variation with del 30SI?
Well, the argument is that in the Archean, when there were no organisms which removed silica from the ocean was, as near as matters, silica saturated. So in the Archean, when BIF was forming, the silica that was forming along with the iron oxides would have this enriched signature and would be different from silica in the modern ocean, which is removed biologically rather than by chemical processes.
Okay, thank you, Professor Rollinson. It was very interesting and informative talk. I strongly believe that our young budding geologists would get inspired from your work and got a lot of enlightened with the knowledge with the talk. Thank you, Professor Rollinson, for a wonderful talk again.
Thank you very much. Thank you for inviting me.
Thank you. Thank you all for attending the seminar.
Okay.
So we had more than 150 viewers for this session live on YouTube.
Thank you very much. Thank you. Okay. Bye-bye.
Bye.
Bye.